Dear students, good morning. Today we'll continue the valence bond theory with respect to few more examples which are mentioned for your studies. Say the fourth example is here, Zn NH3 four times. So you are well familiar, Zn is the central metal ion. It is Zn, atomic number is 30 and its outer electronic configuration is 3d10 4s2 4p0. So during the formation of this complex ion, Zn attains stable oxidation state, that is +2. So that means by losing 2 electrons. 2 electrons means from 4s, the 2 electrons are lost and thereby it attains Zn +2 states and its electronic configuration is 3d10 4s0 4p0. So NH3 being a strong field ligand and it's a neutral ligand and it's also a monodentate, means which is capable of donating a single pair of electrons to the metal ion. So now the electronic configuration of Zn +2 is say same 3d10 4s0 4p0. So the orbital picture, say the d5 3d5 5 orbitals, all the 5 orbitals are completely filled because 10 electrons are there which are distributed, and 4s empty, 4p empty. So according to first postulate of valence bond theory, the central metal ion keeps ready a definite number of atomic orbitals empty. So now here the approaching ligands are 4 in numbers, therefore the metal ion makes 4 atomic orbitals empty, 1 4s and 3 4p orbitals. According to second postulates, they undergo hybridization, and here the type of hybridization is sp3. Okay, so now when the NH3 ligands approaches or interacts with the Zn, say the filled sigma orbital of NH3 overlaps with the empty hybrid orbitals of metal ion. So thereby resulting this complex. Okay, that is Zn NH3 four times. Now here the geometry is decided by the type of hybridization which took place. Okay, so now here sp3 hybridization, thereby the geometry of the molecule is tetrahedral. And now the electronic configuration of Zn +2 in the complex is, now here it is 3d10 4s2 4p6. Actually here after the hybridization there are no more s and p orbitals, they are together said to be sp3 hybrid orbitals. Therefore the electronic configuration of Zn in the molecule is 3d10 4 sp3 raised to 8, because 2 plus 2 plus 2 plus 2, 8 electrons. Therefore the 4 sp3 orbitals, okay, which are having totally 8 electrons. So this will be the electronic configuration of Zn +2. And now there is no unpaired electrons, hence the complex is diamagnetic. Okay, so now you have come across inner and outer orbital complexes. Okay, and they are more common with octahedral geometry, where the coordination number is 6 or where d orbitals are involved in bond formation. Okay, now we'll move on to the next complex, example 5, valence bond theory with respect to NiCN 4 times 2 minus. So similar to the previous examples, here the central metal ion is nickel. So in its ground state, its electronic configuration is 3d10 4s2 4p0. So during the formation of the complex, nickel attains +2 state and its electronic configuration is 3d8 4s0. Here 4s2, these two electrons are lost, therefore it is 4s2 and 4p0. Okay, so now say the electron distribution orbital picture, it is say 3d8 4s0 4p0. So now the hybridization, say the approaching ligand is cyanide ion and it is a strong field ligand, therefore the unpaired electrons. So when the electrons of ligand interacts with the electrons of metal ion, so then being it is a strong field, so it forces the unpaired electrons which are present in 3d orbital of the metal ion to pair up. Okay, so thereby making one of the 3d orbital empty. So you can see here, say this electron is forced to pair up, therefore it is 3d8, okay, by making one d orbital empty. So now the hybridization involves one 3d orbital, one 4s orbital, and three 4p orbital. Okay, so the type of hybridization is said to be DsP2. DsP2. So there are four atomic orbitals because four ligands are approaching, hence four uh, orbitals are required to involve or to bond formation with ligand. Okay, so after bonding, the electronic configuration of nickel in the complex, say we can write down here, say 3d10 4s2 4p4, but actually here now they are no more, say, atomic orbitals, and they are said to be hybrid orbitals. Therefore here, see, the electronic configuration is 3d8, that is of metal ion. Okay, next dsp2 raised to 8. Okay, this will be the electronic configuration of the nickel in the complex. And now there is no unpaired electrons, hence it is diamagnetic, and the type of hybridization is here dsp2, and which decides or which says the structure or the geometry of the molecule is square planar. Okay, this is about the example NiCN 4 times. So now we'll move on to the next one, that is valence bond theory with respect to NiCl 4 times 2 minus. So similar to the previous, here the nickel is the central metal ion, and even here also nickel is in +2 state, and chlorine become or chloride is being a weak field ligand. Here cyanide is strong field ligand, and halide, that means chloride, is a weak field ligand. Okay, so now similar to the previous one, in Ni2 plus the electron distribution is 3d8 4s0 4p0. But here the approaching ligand is a weak field ligand, hence it is unable to force the 3d electrons to pair up against Unstrom. Thereby what happens? They remain as it is. Okay. So now in the nickel, these electrons will not force to pair up because the approaching ligand field is weak field. Therefore it utilizes the next four orbitals. That means 1 4s and 3 4p. Therefore here hybridization is sp3 hybridization. So now after bonding or during the bond formation, say the empty hybrid orbitals of metal ion overlaps with filled sigma orbital of chloride ions, thereby forming NiCl 4 times. Okay. Now two unpaired electrons are present in the d orbital, hence the complex is paramagnetic in nature, and the type of hybridization is sp3 hybridization, and thereby the structure or the geometry of the molecule is tetrahedral. So this much is the explanation regarding, see, the compound or the complex ion NiCl4. Okay, so now we'll move on to the next example in the next class. Okay, thank you.